particle leaves point A with velocity 10 meters per second and deceleration 2 meters per second squared to the right. So here is point A. So a particle leaves this point with velocity 10 meters per second. Now I'm calling this particle particle 1. So u1 is the initial velocity of particle 1. I'm taking directions to the right as being positive, so all vectors pointing to the right are positive. So this particle is moving to the right, so its velocity is positive. However, its deceleration is 2 meters per second squared. So that means that the particle is moving to the right but slowing down. So that means its acceleration vector is pointing in a direction opposite to its velocity vector, its initial velocity vector. A deceleration is a magnitude of a negative acceleration. So the acceleration of particle 1, which I'm calling A1, is minus 2 meters per second squared. So that means that for each second, the speed of particle 1 will decrease by 2 meters per second. So after 1 second, the speed will be 8 meters per second. After 2 seconds, the speed will be 6 meters per second, and so on. Now for particle 1, I'm setting the timer to 0. That's the time particle 1 leaves point A. 3 seconds later, a second particle leaves the same point with velocity 20 meters per second and acceleration 1 meter per second squared to the right. Here is a picture of the situation 3 seconds later. So at t equals 3, a second particle, which I'll call particle 2, leaves point A with velocity plus 20 meters per second. Particle 2 is moving to the right, the positive direction, and its acceleration is 1 meter per second squared. We are not talking about a deceleration here. So the particle is speeding up by 1 meter per second each second. That means after 1 second, the speed of particle 2 will be 21 meters per second. After 2 seconds, it will be 22 meters per second, and so on. Now, at t equals 3, particle 1, of course, will have moved to the right. It'll be at some position over here. We don't know its velocity, but I'm assuming its acceleration is constant. Its acceleration is minus 2 meters per second squared. I'm assuming the same for particle 2. Its acceleration is also constant or uniform. We see that particle 1 is slowing down. Eventually it will stop and it will reverse direction. It will then move to the left with increasing speed. However, particle 2 has positive acceleration. Particle 2 will continue moving to the right with increasing speed. How long does it take for the particles to meet, and how far are they from point A when they meet? Let's say that the particles meet at time t. So here is point A. Here are the two particles meeting at some time t, which we have to find. When they meet, we notice that S1, the distance of particle 1 from point A, equals S2, the distance of particle 2 from point A. So we can think of this as a vector whose tail is at the initial position A and whose head is at the point where the two particles collide or meet. Let's start by getting S1, the position of particle 1 at time t. So we want S1 as a function of time. So at t equals 0, u1 was 10 meters per second. And its acceleration, which is constant, is minus 2. So we have a half of minus 2, which is minus 1. Notice here that when t is equal to 0, that's when we started the timer, when particle 1 left point A, then S1 equals 0. We plug 0 in for t, we get 0 for S1. And that's exactly what we want, because S1 was 0 when t was 0. It's the particle left at the point at t equals 0, so its distance from point A is 0 at that time. Now you might naively think that the formula for S2 is exactly the same as for S1. We're just talking about particle 2. But the problem with this is that if t equals 0 here, then S2 equals 0. If we plug 0 in for t, we'll get 0. And this is not the case, because at t equals 0, this formula is not even defined for the position of the second particle. The second particle is launched at t equals 3, so at t equals 3 we want S2 to be 0. At t equals 3 the particle is at point A, which means its distance from point A is 0. Its distance from point A is S2. But of course, if we use this formula with U2 equal to 20 and A2 equal to 1 and plug 3 in for t, we're certainly not going to get 0. So how do we ensure that when we plug 3 into a formula for S2 that we do get 0? What we do is we replace t in this formula with t minus 3. So this is a very important point. So the time lag is 3 seconds. We could say that particle 2 is 3 seconds behind particle 1 in being launched. So if it's 3 seconds behind, we replace t in our formula with t minus 3. Now, if we plug 3 in for t, we will get 3 minus 3 is 0. We'll get u2 times 0 is 0. Plugging 3 in here will give us 0 squared. Well, that's 0, so the whole thing will be 0. That's exactly what we want. So plugging in for u2, u2 is 20, a2 is 1, so we have half of 1, which is a half. S1 is valid for t greater than or equal to 0. However, S2 is only valid for t greater than or equal to 3. So when t is 3, all of this will be 0. S2 will be 0. And for values of t greater than 3, we will have the position of S2 after it leaves point A. So we need to solve the equation S1 equals S2. So we need to put this expression equal to this expression here and solve for the time. That'll give us the time for the particles to meet. Here is S1. To get, I've expanded out the brackets here. 20 into t minus 3 is 20t minus 60. Squaring out this bracket, we get t squared minus 6t plus 9. We divide by 2 to get a half t squared minus 3t plus 4.5. This is a quadratic equation. We get it into standard form by having 0 on one side. Now we solve this using the minus b formula. So we find that t is minus 7 plus or minus the square root of b squared minus 4ac all over 2a, where b squared minus 4ac is 382. 2a is 2 times 1.5, which is 3. We get two values for t, one positive, the other negative. Now the positive answer is the one we want. We're always interested in a positive value for t. The negative answer will solve the equations. In other words, if we plug minus 8.84 into this equation and then plug it into this side of this equation, both sides will be the same. If you could imagine reversing time, then the particles would meet at t equals minus 8.84. But of course we're only interested in values of t that are greater than 0. That's always what we're interested in. The next thing that we want to get is the distance of the particles from point A when they meet. So we plug the time into either S1 or S2. So I'll use S1, which is 10t minus t squared. We get plus 24.33 meters. What are the velocities of both particles when they meet? Here we have v1, the velocity of particle 1. Its initial velocity is plus 10. Its acceleration, which is constant, is minus 2. So here is a formula giving us the velocity of particle 1 at any time t. Now we're interested in the time of collision, which is 4.18. So plug that in and we get 1.64 meters per second. So at the instant the particles meet, the first particle is moving to the right because its velocity comes out to be positive. It is important to emphasize that this formula is valid for t greater than or equal to 0. Because at t equals 0, v1 is 10. That's what we want, because the timer starts at 0 for particle 1. Now, let's look at particle 2. It is incorrect to write this down, because we want the velocity of particle 2 to be valid for values of t that are greater than or equal to 3. We want the velocity of particle 2 to be 20 when t is equal to 3. So t equals 3, the particle 2 leaves point A with a velocity of 20 meters per second. If we plug 3 into this formula here, we are not going to get 20, we're going to get 20 plus 3, which is 23. So if we plug in t equals 3, we get v2 equals 23, which is incorrect. So like before, when we were getting the distance of particle 2 from point A, we have to replace t with t minus 3. So this means that when particle 2 starts out from point A, starts out at t equals 3, then v2 will be got by plugging 3 in for t. And of course we'll get 20 plus 3 minus 3, or 20 plus 0, which is 20. And this is what we want. So u2 is 20, a is 1. We replace t with t minus 3. So our formula for v2 simplifies down to 17 plus t. So this gives us the velocity of particle 2 at any time t. And by the way, this formula is only valid for values of t greater than or equal to 3. For values of t less than 3, this formula makes no sense because the particle hasn't started on its journey. It starts at t equals 3. So now we can go and get the velocity of particle 2 at the time when the particles meet, which is 4.18. We get 21.8 meters per second. This is positive, which means that the second particle is also moving to the right when the particles meet. The second particle is behind the first particle, so I'll just try to show the second particle's velocity. And the first particle's velocity is 1.64, much smaller. The first particle's acceleration is negative. In other words, it is slowing down by 2 meters per second each second. So eventually particle 1, which is here, will come to a halt and it will reverse direction. It will move to the left with acceleration 2 meters per second squared. However, particle 2 will continue to speed up because particle 2's acceleration is positive. So if the particles can pass through each other, then v2 will overtake v1 and continue moving to the right with increasing speed, whereas particle 1 will stop and reverse direction and move to the left with increasing speed. Now let's look at the velocity time graph for the particles. Let's look at the velocity of particle 1. This formula is valid for t greater than or equal to 0. So we can plug 0 in here and of course we get v1 equals 10. That's the initial speed of particle 1. This is the graph of a straight line. When we're dealing with constant acceleration, the velocity time graphs are straight lines. The slope is -2, so the line has negative slope. It's sloping downwards. If we set this equal to 0, we get t equals 5. So at t equals 5, we have a point on v1. So you could pick 2 points on a line, pick the points where the line cuts the axes. Here we let t equal 0 and we get v equals 10. For this point we let v equal 0, so we have 10 minus 2t equals 0, so t equals 5. So you can see the slope is -2. The rise divided by the run, 10 over 5 is 2, is the magnitude of the acceleration, but the line is sloping downwards, so the acceleration is -2, the slope is -2. Now, as for v2, it is valid only for values of t greater than or equal to 3. So the velocity time graph for particle 2 starts at t equals 3. The initial velocity for particle 2 is 20. So t equals 3. We see v2 is 17 plus 3 is 20, which is what we have here. That's what we're given. So we go up to 20 at t equals 3. We could pick a second point on this by setting t equal to, say, 5 or 4 or whatever we like, any number bigger than 3. Or we could look at the slope. The slope is plus 1. So that means that the line is sloping up the way. It's got positive slope. If we increase t by 1, then v is increased by 1. 1 over 1 is 1, the slope of the line. We see that the velocity of particle 2 continues to increase. It increases indefinitely. However, we see that at t equals 5, the velocity of particle 1 is 0. So at t equals 5, particle 1 stops and reverses direction. So then its velocity becomes negative for values of t greater than 5, because now particle 1 is moving to the left. And again, it moves to the left indefinitely with increasing speed. The velocity is decreasing, it's becoming more and more negative, but the speed, which is the magnitude of the velocity, is increasing. So particle 1 is moving to the left with increasing speed, but decreasing velocity. The next thing that we will look at are the distance time graphs. So these were the distances of the particles from the origin. And rather than try to plot these by hand, I'm just going to use Wolfram Alpha to plot them for t equals 0 to t equals 10. For the second particle, there was a time lag of 3 seconds. It started out when t was equal to 3, so this is only valid for t greater than or equal to 3. So we replaced t with t minus 3. So we can ignore this part here. So this is what the graph of S2 should look like. So we're plotting S against time. At t equals 3, S2 will be 0. If we plug 3 in for t, all of this will be 0. That's what we want. I'm after wiping the picture associated with the second particle. But if you think back, at t equals 3, the second particle started out. So its position was 0, S was 0. However, we know that particle 1 started out at t equals 0. At t equals 0, S1 was 0. So this graph starts at the origin. We also saw that at t equals 4.18, the particles meet. So the distances of both particles from point A, which is the origin, are the same. And we found that distance to be 24.33 meters. Both of these graphs are quadratic functions, so the shape of the curves are parabolas. This function here has a positive t squared term, so that's why it's an upward or an upright U shape. Actually, it looks more like a straight line here because of the scales. The second function has a negative square term, so it is an inverted U shape. We can see that S2 continues to increase with increasing time because the second particle is moving further and further to the right with increasing speed, so that's no surprise. However, for particle 1, we can see that as from time t equals 0 to t equals 10, the particle has been moving to the right, but at t equals 10, at t equals 10, S1 is 0. So, as a matter of fact, for the first 5 seconds, particle 1 was moving to the right. Its distance from the origin was increasing. See, it started off with 0, and it increased to some maximum value at t equals 5 actually. Then its distance from the origin point decreased for t between 5 and 10. So that means after t equals 5, the particle is moving back towards the origin. At t equals 5, it stops momentarily. Its velocity is 0 at t equals 5. And after t equals 5, its velocity actually decreases. We can see it from the velocity time graph. At t equals 5, the velocity is 0, and after t equals 5, the velocity becomes negative. So we can see now the distance s from the origin is decreasing as particle 1 goes back to the origin. That's the origin is point A. And at t equals 10, the particle is back at point A. S is 0.